Well, let us take some examples. Let us project a particle with velocity v0 at an angle of theta naught with respect to horizontal. In gravity, it will move in a projectile path, a parabolic path which is parabolic in nature. We need to calculate the angular momentum of the particle as a function of time and angular momentum of the particle as a function of x distance with respect to the point of projection. In one method, we can proceed by using the equation torque is equal to rate of change of angular momentum about any reference point, where angular momentum of the particle at time t can be written as L naught or L, angular momentum of the particle at time t. The net force acting on the particle is mg. Since the torque acting on the particle about O due to gravity is equal to mj into this x distance, because this r vector, this is mg vector, r cross mg, let it be phi. So this angle is, say this is theta, phi by 2 plus phi. R cross mg is equal to r mj, the sine of the angle between r vector and mg vector, and the angle between these two vectors is equal to pi by 2 plus phi. That's equal to cos phi multiplied with rmj, but we know that r cos phi is equal to x, mg into x, and direction wise r cross mg, clockwise or in minus KAB direction, or directly you can just write mj into the perpendicular distance from the reference point onto the line of action, and direction is minus KAB. Equation number 2. Substituting tau from equation 2 in equation 1, we get minus mg x KAB is equal to rate of change of angular momentum of the particle with respect to O. This gives us dLO is equal to minus mg KAB x dt. Let us integrate both sides. dLO, integration of this is equal to minus mg KAB vector x dt. We know that the horizontal component of the velocity The horizontal component of the velocity of this particle remains conserved because there is no force acting along the horizontal direction, assuming no air resistance or any viscous force. Therefore, x is equal to v naught cos theta naught into t. Substitute here. This will give us mg kf v naught cos theta naught into t dt. At time t equal to 0, the angular momentum will be 0 because the particle was here. When the particle is here, the r vector or the x vector is 0 with respect to this point. Therefore, the angular momentum becomes 0. When the particle comes to this position, having the velocity v, its angular momentum let be L. So, L vector is equal to minus mg kf v naught cos theta naught t dt integral 0 to t. This gives us minus mg v naught cos theta naught into t square upon 2 into kf. Answer. This is the angular momentum of the particle as a function of time. And if you substitute v naught cos theta naught into t as x, we can get mg v naught cos theta naught, and instead of t you can put x upon v naught cos theta naught square by 2, or we are getting minus mg x square kf upon to v naught cos theta naught. So, angular momentum about this point of this particle in terms of t is minus mg v naught cos theta naught t square by 2 in minus kf direction or clockwise direction. And as the function of x distance, it will be minus mg x square by 2 upon v naught cos theta naught kf, or in negative z direction, or it is clockwise, or it is inward. In this way, you can understand that angular momentum is directly proportional to the square of the time, also directly proportional to the square of the x distance. That is the idea. Let us take another example. You take the sun planet case. This is the sun, this is the planet. The maximum distance is b and the minimum distance is a. Let us calculate. Here velocity v1, here velocity v2. Let us find the ratio of velocities, ratio of accelerations, ratio of kinetic energies, ratio of gravitational potential energy of the planet at these 2 points, and ratio of forces. and the ratio of angular momenta. Ratio of linear momenta. Let us assume that here the velocity is v1, here velocity is v2. Ratio of the velocities. The starting point is based upon the conservation of angular momentum principle. Since net torque is 0 as I explained, angular momentum of the planet can be conserved. So, angular momentum at this point 1 is equal to angular momentum of the planet at this point 2. Here angular momentum is m v1 into a. Here angular momentum is m v2 into b. It's getting cancelled. v1 upon v2 is equal to b upon a. Answer. For acceleration, here the force acting is F1, here the force acting is F2 due to the sun. So, acceleration 1 at point 1 upon the acceleration at point 2 is equal to F1 by m upon F2 by m. According to Newton's second law, we are getting the ratio of the forces, and here the forces J. Let us assume that small m and capital M are the masses of the planet and the sun respectively. So, F1 can be written as gmm by a square and F2 is gmm by b square according to the law of universal gravitation of Newton. So, these two will get cancelled. You are getting b square upon a square. Answer. The kinetic energy ratio is equal to half m1 v1 square upon half m2 v2 square. But these two masses are equal. So, it is just v1 upon v2 square of this. But v1 upon v2 is equal to how much? b by a square. Answer. And potential energy E1 upon U2. The expression for the potential energy of interaction between two masses in gravity is given as gm1 m2 by r square. Here m1 m2 is small m into capital M, and r is for this position A, and here for this position the r is B. In this way, if you get cancelled, this numerator term g small m into capital M, you are getting b square upon a square. Answer. Now, let us calculate the force. As we know, the force is directly proportional to the product of the masses and inversely proportional to the distance of separation between the sun and the planet. Therefore, F1 by F2 is equal to gmm by a square by gmm by b square is equal to b square upon a square. Answer. Come to the angular momentum. Since angular momentum at 1 and 2 are equal, L1 upon L2 will be equal to 1:1. And linear momentum P1 upon P2 is equal to mv1 upon mv2. So, mm getting cancelled and you are getting v1 upon v2, that is equal to a b by a as we calculated earlier. The central concept is conservation of angular momentum. For this example,